So this time we're doing problem 29 from chapter 5, and the question says, a 45 kilogram crate of tools rests on a horizontal floor. You exert a gradual increasing horizontal push on it, and the crate just begins to move when your force exceeds 313 newtons. Then you must reduce your the pushing force, to 208 newtons to keep it moving at a steady 25 centimeters per second. Part A asks, what are the coefficients of static and kinetic friction between the crate and the floor? So we have a box on the floor that's getting pushed. We know that the box has a mass of 45 kilograms. And we know the initial force is 313 newtons is what's required to get the box moving. And to keep it moving, the force then has to go to 208 newtons. So from that, we can find the coefficients of static and kinetic friction. We're going to use this force for the static friction and this force for the kinetic friction. So the force of static friction is going to be equal to the coefficient of static friction times the mass times gravity. So that's going to become 313 times mu times 45 times 9.8. We're going to have the same thing for kinetic friction, the force of kinetic friction, but it'll have a different coefficient because it requires a different force. Mu 45 times 9.8. So when you do the math for both of these and solve for mu, you get that mu is equal to, mu for static friction is going to be equal to 0.7091, and mu for the kinetic friction is going to be equal to 0.47. So those are your answers for part A. Part B asks, what push must you exert to give it an acceleration of 1.1 meters per second? So for part B, we're going to be using Newton's second law. So what force has to overcome the force of kinetic friction times the mass, the acceleration. And so we're solving for this force. So we know that that force is going to be equal to the mass times the acceleration plus the kinetic friction. And that'll give us the force that we have to push to overcome. So when we plug our variables in, we know that the mass is 45 kilograms. It tells us the acceleration that it wants. And then we know the kinetic friction because it's given at the beginning. So then you just plug the numbers in and do the math. And that comes out with a force of 257.5 newtons for part B. Part C then asks, suppose you were performing the same experiment on the moon, where the acceleration due to gravity is 1.26 meters per second. What magnitude push would cause it to move? And what would its acceleration be if you maintain the push from this part? So it wants to know the two frictional forces that you would have on the moon, and then what your acceleration your acceleration would be if you did this, you got exerted this force on there. So these equations are gonna be the same, except for we're solving for the forces, because even though it's on the moon, the coefficient of static friction between the board and the box is still gonna be the same, or the floor and the crate of tools, I guess. So we're still gonna use those. So 0.7091 times 45 kilograms times 1.662 for the acceleration on the moon. And then for kinetic friction, 0.47 times 45 times 1.62. That gives us a force of static friction that is going to be equal to 51.7 newtons for our static friction on the moon. I guess it doesn't want both of them. I was mistaken. It just wants how much force you would have to push to cause it to move. So we're then going to use this. And that force is then going to be equal to so that is the force that would cause it to move. Sorry, I got confused. That's how much force you'd have to put on the box to make it move. It'd have to be greater than that. So then, if we wanted to find the acceleration, if we use this force, so the equation is going to be the force minus the kinetic friction divided by the mass is going to be equal to our acceleration. So this is the part where we need to find the kinetic acceleration. And so when you plug the variables in, 2.8 minus 0.47 times 45 times 1.62, all of that divided by 45, and 45 will give you the acceleration. And so your acceleration, when you do the math, comes out to 4.96 meters per second squared. And that's your answer. And it is a faster acceleration on the moon than what we were given on Earth, and that makes sense because there's less gravity.